Section 12.2, Analysis of Variance. Previously, we learned how to compare a mean to a specific value. So when we first started with hypothesis testing, we were testing whether mu was equal to some specific value versus whether it was bigger than that value or less than. That would indicate a one-tailed test, or just not equal to it at all, or a two-tailed test. And depending on the size of the sample and whether we knew the value of the standard deviation sigma, we used a z-test or a t-test to determine if the sample mean was close enough to the specific value we were testing. If instead we are interested in comparing the means of 3 or more populations against each other, then we use a completely different technique called analysis of variance, commonly abbreviated as ANOVA. So the AN for analysis, O for VA for a variance, ANOVA. So it has to be 3 or more. There are other methods to compare just 2 populations, but this one is specifically for 3 or more. To do an ANOVA, we will use the F test to complete it. And just as before, with our previous hypothesis testing methods, we have to set up our null and our alternative. So here, the null is going to be that all the means are the same. So the mean from sample 1 is the same as the mean from sample 2, is the same as the mean from sample 3, and so on and so forth for however many categories that we have. And remember here, we're not saying that they're numerically exactly the same. We're saying that they're close enough that there's not a statistical difference. But basically, all the means are the same. It's what we're setting up for the null. For the alternative, at least one mean is different from the others. Only one has to be kind of the bad apple, if you will. And if it's significantly different and we can't explain it just by chance, then we would reject the null and say that at least one mean is different. Now, although we're comparing means, the F test is taking a look at the variances of the populations in 2 ways. One way is looking at the variance between the groups. So this involves finding the variance of the means. Now, remember, variance measures the spread. And what I'm doing is I'm looking at the means, and I'm kind of taking an average of those and then finding the variance. And hopefully, if the means are very, very close to each other, the variance will be very small, indicating that there's not a lot of spread. So that's one way that we're going to take a look at our data. The other way is looking at the variances within the group. And this involves finding the variance of all the data. So what I do here is I find the variance, the mean and the variance. I put all the data together regardless of what grouping or category it came from, and I find the variance again. Now, if there's little or no difference among all the means, meaning they're pretty much homogeneous, then the between group means will be almost equal to the within group means, and the null hypothesis will not be rejected. So then we would be able to say, yeah, they're pretty much the same. But on the other hand, if any of the means differ significantly, the between group variance will be a lot larger than the within group variance, and that's when we would reject the null hypothesis. So even though we're interested in the means, our hypothesis is set up with the mean 1 is equal to mean 2, we're actually comparing variances, and that's where the name comes from for this test, analysis of variance. Now, just as before, with our other hypothesis testing methods, we have to have a few assumptions in place. With ANOVA, we want to assume, we want to make sure, rather, that the populations are normal or approximately normal. This one's kind of loose. They don't have to be exactly bell-shaped, but we want some type of normality there. 2, the samples must be independent of each other. So the groupings can't have some relationship between them. They have to be completely independent. And 3, the variance of the populations must be equal. Okay, now before we actually get to conducting an ANOVA, let's practice finding F values, because that's a little bit different. Now, an F table is another skewed distribution, kind of like chi-squared, so it's going to look something similar to this. And notice that I don't go past that y-axis, so there's no negative values, just all positive values, and I have the skewness in the tail, or skewness to the right. The F value that we're comparing and testing is found by taking the ratio of the variance between samples that we just talked about with the variance within samples, and I'm going to put a fraction with those two values. So F is the same thing as the variance between the samples compared to the variance within the samples. And because we're finding the F value that way, we need two values for degrees of freedom. So previously with chi-squared we only needed one, but here we need two. So one of our degrees of freedom is going to come from the numerator. Well, remember the numerator is dealing with the variance between the samples. So for the degrees of freedom for the numerator, we're interested in the number of groups, k minus 1. So it's kind of similar to what we saw with chi-squared. So degrees of freedom in, degrees of freedom numerator is the number of groups, k minus 1. So if I have 3 groups, then my degrees of freedom for the numerator would be 2. Next, we need the degrees of freedom for the denominator. Well, remember that's talking about the variance within the sample, so that's all the data. So the way I find this one is the sum of all the sample sizes, n, how large that is. So if you forgot, capital N is the sum of all the little sample sizes. So for each group, I'd add those all up, minus the number of groups k. So if you just remember that as capital N minus k, that's the degrees of freedom denominator. So I have to have those two numbers in order to find the value on the F chart. And as far as when we go to look at our picture, the F test to compare means is always going to be in the right tail. So I don't have to worry about dividing by 2 or is it in the left tail. This is always going to be assumed to be right-tailed. So let's take a look at example 1. This is just practicing finding those F values before we move on to the ANOVA. So in A, I have an alpha of 0.05, degrees of freedom numerator of 10, and degrees of freedom denominator of 12. Now you do have a table in the back of your book, but it's pretty limited. It only does 2 values for alpha. And I found one here on the internet, and the link is right here in the so feel free to go to that site if you want access to this table. But notice how in our example here we were given alpha first, and that's because you have to identify which table you're going to use. So we were given alpha of 0.05, so I first want to identify the 0.05 table. So here you notice that alpha is 0.1, so the next one probably should be, there we go, there's 0.05. And degrees of freedom numerator are running across the top, degrees of freedom denominator are running down the side. So we had 10 and 12. So here's 10, and I'm going to go down to 12, and it looks like that's the value there. Yeah, degrees of freedom 10 and 12. So I have 2.7534. Okay, let's try another one. Alpha is 0.01, degrees of freedom numerator, so this is the F value, let me say that. Okay, degrees of freedom numerator are 6, and degrees of freedom denominator are 7. So first I have to identify, and so I need 0.01 this time. There's 0.025 and 0.01, and we're 6 and 7. So I go across to 6 and down to 7, and we have 7.191. Okay, so that's it to find an F value. Identify the alpha first because you have to know which table you're looking on. Degrees of freedom numerator across the top, degrees of freedom denominator down the side, and wherever those two intersect, that's your F value. Okay, now recall we stated that to compute the F value, we are comparing the variance between samples with the variance within samples. So that's what we just saw up on the previous page, that ratio there. Well, there are lots of calculations that go into that statistic. We need the mean of each group, the variance of each group, the mean overall, and some more. With ANOVAs, it's customary to let technology like a computer program such as SAS or Minitab or even Excel, or even our calculators handle those calculations. So in our notes here, we're just going to concentrate on making some of the final calculations and then making the decision about the test. Example 2. A researcher wishes to see if there is any difference in weight loss if participants put on one of 3 special diets. Participants are randomly assigned to one of 3 groups and placed on the diet for 2 months. The weight losses in pounds are shown in the table below. More specifically, this is a summary of the weight loss. So we're not given the raw data here. We're told what happened to the participants in diet A, diet B, and diet C, and all we know are the mean and the variance. So A, we had 4 people who participated. The average weight loss was 5 pounds, and the variance was 3.3 pounds. Okay, from that data, we are being given the F value of approximately 7.74, and we have a few things to do here. So A, find the degrees of freedom, shouldn't have the word there, find the degrees of freedom of the numerator. Well, remember the numerator comes from between the means. So this one is asking how many categories there are. So we're looking at how many categories there are, but for degrees of freedom, it's 1 minus that. So K is 3, but for degrees of freedom, we say 3 minus 1, so we have 2. Part B, find the degrees of freedom of the denominator. Well, this is where we want all the data minus K. So this is N minus K, capital N minus K. N would be 4 plus 6 plus 4. So it's everybody regardless of which diet they were on, and that's 14. So then if I take 14 minus 3, be really careful, and I'll probably almost make the same mistake. You're not subtracting the previous degrees of freedom. You're subtracting the number of categories. And there were 3 different diets. So it's 14 minus 3, which is 11. Okay, determine the critical value at 0.025 level of significance. Let's move down here. So what I'm looking for is an F value, knowing that I have degrees of freedom 2, 11, and alpha equal to 0.025. And remember, we have to identify alpha first because that's going to tell us which table to use. And so we come back up here, 0.025. And for the numerator, we have 2 and the denominator 11. So it looks like our value is right here, 5.2559. Okay. And then D. From the diet data, can we conclude that at least one of the groups differs significantly from the other in mean pounds of weight loss? So this is where we're making the decision whether to reject or accept or fail to reject the null hypothesis. Now, very similar to all the other hypothesis testing you've done, I have to compare the F they gave me, 7.74, to this critical value here. And I know some of us are a little more visual, but remember we have the skewed distribution, and my critical value, what I found from the table, is here at 5.2559. So this area in the tail beyond that value, this is my rejection region. So if I have a test value that falls in there just like before, I'm going to reject the null hypothesis. Well, they told us that the F value was 7.74. And that does fall in the rejection region. So my conclusion, and we weren't asked for this specifically, but this is a good way to keep all your information straight. We reject H naught and conclude at least one group has a mean weight loss that is different than the others. So even in your homework, you're not asked to kind of make this make a statement about rejecting or failing to reject the null hypothesis and then making a conclusion, make sure you get in the habit of that for a written exam, because you want to be able to write out what your conclusion is. So here we reject H0 and conclude at least one group has a mean weight loss that is different from the others. So in order to answer the question in D, let's be careful with how it's worded. From the diet data, can we conclude that at least one of the groups differs significantly from the others in mean pounds of weight loss? Yes. One of them is different. That's what we concluded because we rejected H0.